Alright, so this section, section 3.4, we're going to work on solving equations that include exponential and logarithmic expressions. So solving an exponential equation by expressing each side as a power of the same base just simply means, and we've looked at some of these, if we have b to the m power and it is equal to b to the n power, since both of these bases are the same, if the two expressions are equal, that means that m must equal n. So any kind of equation we've got, if we can write that thing as an exponential of the same base on both sides, then we can get it to the point where we can set the two exponents equal and solve for any variable we might have. So for instance, right here, with this one, if we have 2 to the 3x minus 8 equals 16, I want to take whichever one of these is the larger number and see if I can express that as an expression of the base of a base of this one. So 16 I can't express as a 2 to some power because 16 is 2 to the 4th power. 2 times 2 times 2 times 2 times 2 equals 16. So that means we have 2 to the 3x minus 8 being equal to 2 to the 4th. Well, once again, if the bases are equal, and the sides are equal, then the exponents must be equal too. Therefore, 3x minus 8 must be equal to 4. And at that point, we can just move stuff around and solve for our variables. So we're going to add 8, get 3x equals 12, and which means x equals 4. And then you can always go back up here and check. 3 times 4 is going to give you 12. 12 minus 8 gives you 4. 2 to the 4th power is equal to 16, so it does check out. With this one, we can look at the larger one and see, can I express 27 as an exponential of base 9? And you can't. There's not one that's going to be easy. So in this case, we're going to have to do both of these. Both of these things are just powers of 3. So we can go ahead and think of 27 as 3 to the 3rd, and that's the 27, and it's raised to the x plus 3 power. And over here, 9 is 3 squared, and it's raised to the x minus 1 power. So as long as our parentheses here are equal to what we started off with, we're good. Now, don't forget, now that you've got the common base of 3, you've got to need to simplify your exponents. Remember, if you're raising a power to a power, you multiply. So 3 times x plus 3 is going to give you 3 to the 3x plus 9. And over here on this side, same thing. We're going to have 3. When we raise the power to the power, we multiply. So we get 2 times x minus 1, which is 2x minus 2. So same base. The two sides are equal. Therefore, the exponents must be the same. They must be equal as well. 3x plus 9 equals 2x minus 2. Doesn't matter which way you're going to carry everything. I'm going to carry my x's over here. I'm going to subtract 9 from both sides. Minus 9 minus 9. And that's going to give me 3x equals 2x minus 11. Move that x to the other side by subtracting 2x. Subtract 2x. And we're going to get x is equal to negative 11. Alright, and you can go up here and check as well. Negative 11 plus 3 is going to end up giving you what? Negative 11 plus 3 gives you negative 8. So 27 to the negative 8 power is equal to 9 to the negative 11 minus 1. So 9 to the 13th power. Sorry, negative 12. Is that right? Yeah, negative 12. All right, now you can also use logarithms to solve exponential equations by isolating the exponential expression. Take the natural log of both sides, or the log that makes the most sense. Typically, you're going to use natural log on both sides for bases other than 10. If your base is a 10, then you can take the common log. And then simplify using one of the following properties. Well, the natural log of b to the x is x times the natural log of b, or the natural log of e to the x is x, or the natural log, or the common log of 10 to the x is x. And then solve for the variable. So here we've already isolated the exponential expression. So we're going to take the natural log of both sides. Since we have a base other than 10, so we're going to have the natural log of 4x is equal to the natural log of 15. And that's supposed to be to the x power. So then we can use the power rule for logs and move that out front, and we get x times the natural log of 4 equals the natural log of 15. We want to solve for x, so that means we're just going to divide both sides by the natural log of 4. So x is going to be the natural log of 15 divided by the natural log of 4. Now, if it's a calculator problem, you can go ahead and solve that and find out what it's going to be, but you're not always going to have to do that. And in this case, the answer is approximately 1.953. All right, now with this base over here, with this problem over here, since we have a base of 10, we can actually use the common log. And if we use the common log of 10 to the x power equals the common log of 120,000, well, we can use that power rule for logs again. And x times the common log of 10 equals the common log of 120,000. Well, the common log of 10 is just going to be 1. Remember, it's 10 to what power gives you 10? So that's going to be 1. So x is equal to the common log of 120,000. Now, guys, you could also have used the natural logs as well. Let me get you an approximate answer on this. You get the log of 120,000. It's 5.079. Now, I'm going to show you that it works the same way with natural logs as it does with common logs. So, same problem, just working a little different way. If I take the natural log of both sides, I get this. And then the same way I did before with both of these, I'm just going to move that x out front. So x times the natural log of 10 equals the natural log of 120,000. And then, of course, the natural log of 10 is just a number. I want to solve for x, so I'm going to divide both sides by natural log of 10. So when I put this in my calculator, guess what I get? I get the exact same number that I got before. And of course, this decimal goes on. I just stop at 3 decimal places because that's pretty much as far as you got to go for right now. Now, of course, you know they're not all going to be that easy. So you're going to have some manipulation you're going to have to do and some things like that. So in this case, we want to, remember, you want to isolate your exponential first. So we're going to get solved down to e to the 0.6x. So that means I'm going to add 3 to both sides. So you get 40 e to the 0.6x. 237 plus 3 is 240. Then you want to divide both sides by 40. So e to the 0.6x, 240 divided by 40 is going to be 6. Now we can take the natural logs of both sides since we've actually isolated our exponential. Natural log of e to the 0.6x equals the natural log of 6. And the natural log of e to the 0.6x gives you 0.6x. And you can do the power thing and all that. Move that out front, and the natural log of e is just 1, so that's where we get the 0.6. And then over here we've got the natural log of 6, and we would divide by 0.6. So x is going to equal natural log of 6 divided by 0.6. And of course you can plug that in your calculator. And you get 2.98. 6. Alright, I want you guys to pause the video and try this one. I'm going to work it out and I'll show you the answer, but I want you guys to try it without looking at the answer first. And I'll show you the answer in 3, 2, 1. Alright, so here's what the answer is. This is probably where you stopped, but I want to show you something. We got 1/2 natural log of 9. Well, you can do more simplification of this. If you take that power and move it up there, we're going to get the natural log of 9 to the 1/2 power. Well, what's a 1/2 power? It's a square root. So what's the square root of 9? So this is the same thing as the square root of 9, which is the natural log of 3. And you should look for ways to break that down like that. Alright, so this one is a little more complicated than the other ones we've dealt with, but it's not too bad. We've already got exponential expressions on both sides. They are isolated, so we're good by just taking the natural log of both sides. So we get the natural log of 5 to the x minus 2 equals the natural log of 4 to the 2x plus 3. Now then we can use our power rule, and we're going to move those powers out front. So we get x minus 2 times the natural log of 5 equals 2x plus 3 times the natural log of 4. Now guys, be real careful here, because you're going to want to just move that thing out there in front and not put parentheses around it, but there's a big problem with that. You're going to forget that you've got to multiply this natural log of 5 times both those terms, and this natural log of 4 times both those terms. You've got to distribute that now, and you'll see why in just a second. But if we distribute that natural log of 5, which is just a number, it's like 3. It's the same thing. It's just multiplying these things times some number. It just happens to be in an ugly form we don't like. So we've got x times the natural log of 5 minus 2 natural logs of 5 equals, and do the same thing over here with the natural log of 4, 2x natural log of 4 plus 3 natural logs of 4. Now, what you want to do is you want to get your x terms together and get everything else on the other side. So I'm going to move this one over there, and I'm going to move that one over here. So I'm going to add 2 natural logs of 5, and I'm going to subtract 2x natural logs of 4 from both sides. Alright, so at that point, we know these are going to cancel out. We know those are going to cancel out. So we have x natural logs of 5 minus 2x natural logs of 4. And over here, we have 2x natural log of 5 plus 3 natural logs of 4. Now guys, if you mix these up and put the 3 natural log of 4 in front, it's perfectly okay. That's still the same thing because they're both positive numbers. Now, what do we know we have in common over here? Well, we have a common x that's multiplied in both of those. That means it's a common factor and can be factored out. So if we take out that x, we're going to have the natural log of 5 minus 2 natural logs of 4 times this x is equal to this same crap we had over here before because we didn't do anything to it. And then, of course, what are you going to do when you want to solve for x? You're going to divide by this big thing right here. So you got x is equal to what's... Hold on. Oh, there's not supposed to be an x in there. Sorry about that. I copied that part over there when it's just supposed to be 2 natural logs of 5 that I'm adding to that side. So anyway, we got 2 natural logs of 5 plus 3 natural logs of 4 divided by everything we've got right there. Natural log of 5 minus 2 natural logs of 4. Now, guys, do not go in there and start thinking, oh, I can cancel out the natural logs of 5. No, you can't. They're not common to everything on top, and there's more than one term on bottom. So that's as far as you can go. Now, you could grab your calculator and, calculate, use it to find out what the answer is, but most of the time you're not going to have to do that. All right, now I want you guys to try this. I want you to pause the video as always and try it by yourself, see what you can come up with, and check and once you get it worked out and you want to check your answers, you can start the video back and check your answers, and I'll show you the answer in 3, 2, 1. All right, so here's the answer. Check your work. If you got it wrong, or if you if you got part of the way through and didn't get a chance to finish it, or kind of got stuck and wasn't able to finish it, see where you went wrong. Make sure you get this copied down, because you will see problems like this on the test, I can promise you. So then, of course, we could just take our calculator and find all these values, and you could get the value to however many decimal places you needed it, if you needed to. This would be a good one for me to give you without a calculator, and you could just leave it in that form right there, though. So, just because you need a calculator for the natural log of 3, don't think that you're going to have a calculator for these problems, because you're not. Natural log of 3, written as natural log of 3, is actually an exact answer. It doesn't lose any decimal accuracy or anything. So this is an actual exact answer, where a decimal is just an approximation. Now, if it specifically tells you to use the calculator to obtain a decimal approximation, go ahead and do that, and however many decimal places it says. In this case, it says 2 decimal places. So I guess I could find that out for you, couldn't I? So the natural log of 3 plus the natural log of 7. All right, that gives me 3.0445, and I'm going to divide that by 2 natural log of 3 minus natural log of 7. All right, and I got 12.114. And while it says 2, I like to carry it to 3 because, well, 3 is AP standard, so I'm always in the habit of doing 3 decimal places accurate, so that's why. All right, now you're also going to see problems like this, and this, as you look at this, you're probably thinking, oh, well, that kind of looks a little familiar. Well, the reason it looks familiar is because it's in the form of a quadratic formula, of a quadratic expression, where we have this being x squared minus 4x plus 3. So you can actually think about this as e to the x squared minus 4 times e to the x plus 3 equals 0. So in this case, our x is actually e to the x. But guess what? You can still factor it the same way you did before. So you can go in here and you can write in place of e to the x, why don't you put y, if it makes it a little easier for you to remember and see what to do with this. Now you can factor this, and you're going to have y and y. Same signs, both minus, minus, minus. Numbers that multiply to give me 3, but add to give me 4. That would be 3 and 1. And then now, since up here I let y equal e to the x, I'm going to let e to the x equal y, and you get e to the x minus 3 times e to the x minus 1 equals 0. Now, once you do this, what do we know we would have done to solve for y's here? We would have set y minus 3 equal to 0, and we would have set y minus 1 equal to 0. It doesn't change. It's the same thing here. So e to the x minus 3 equals 0, and e to the x minus 1 equals 0. And then we just solve these like we have been. So you're going to move the 3 over, move the 1 over, and e to the x equals 3, and e to the x equals 1. And then all you've got to do is do the natural log of both sides to find out what x is. So x is going to be the natural log of 3, and over here would be the natural log of 1, which is, of course, 0. So the solutions are x equals the natural log of 3 and 0. And you can always go back up here and plug those in and find out. But that is the case. All right, now you can also use the definition of a logarithm to solve logarithmic equations. So we know that we can take the log base b of m equaling c, and we can rewrite that to be b to the c power equals m. Once we get it in an exponential expression, it's a lot easier to solve. Now, you do need to check proposed solutions in the original equation, because you cannot take the log, remember, of a negative number. So if your m that you come up with, or your solutions that you come up with, makes this a negative number, you've got to throw that solution out. All right, so let's look at a real quick here. We've got 4 squared equals x plus 3. So x plus 3, of course, is going to be x plus 3. 4 squared is 16. 16 equals x plus 3. We're going to subtract the 3, and we got x is equal to 13. Now, always go back and plug in. If I plug in 13 right here, 13 plus 3 gives me 16. What is the log base 4 of 16? Well, 4 to what power would give you 16? And ta-da, it is 2. So it does check out. Now, with this one over here, we've got 3 times the natural log of 2x equals 12. You want to isolate your log first. So you want to get rid of that 3. So we're going to go ahead and take that 3 and divide both sides by 3. So the natural log of 2x is going to equal 4. Now, we know that we've got an e down here that's understood. So e to the 4th equals 2x. And then once we get there, we can divide both sides by 2. And we know that x is going to be e to the 4th divided by 2, or 1/2 e to the 4th. And you can find out what that decimal was if you needed it. All right, so for this one, we're going to have to use some of those properties we've learned. We're going to have to combine the two logs on this side. So the log base 2 of x plus the log base 2 of x minus 7 gives me the log base 2 of x times x minus 7. Well, of course, that's going to give you the log base 2 of x squared minus 7x. Still equaling 3. So now then we do our transformation into the exponential, and we're going to have 2 to the third is equal to x squared minus 7x. So that, of course, is going to be 8. And we can move that to the other side. And then we're going to factor. So over here we're going to have x and x. Different signs, 1 plus, 1 minus. Numbers that multiply to give you 8 and subtract to give you 7. Of course, that's going to be 8 and 1. And the larger number is going to be minus. So minus 8 and plus 1. All right, so we have solutions of x equals -1 and positive 8. All right, but at this point, you've got to go back and you've got to look up here and make sure that both of these solutions do fit into that possibility. If I take 8, I can take the log base 2 of 8, no problem. I can take the log base 2 of 8 minus 7. It's still a positive number, it's 1. But the -1's a problem, because I can't take the log base 2 of -1, and I can't take the log base 2 of -1 minus 7, which is -8. So I actually end up tossing that value out. So the solution, the only solution, is x equals 8. Remember, you cannot take the log of a negative number, no matter what the base is. So that's where you end up tossing things out. A negative number or 0. All right, now the last property we're going to talk about is using the one-to-one property of logarithms to solve logarithmic equations. And you've done a little bit of this. It's very, very similar to, actually, let me take that back. No, you haven't done any of these. But it's very similar to the exponential one-to-one property, where we were saying that if the bases were the same, then the exponents had to be the exact same, and we were able to solve it. Well, it's the same thing here with the logs. If you can express the equation in the form log base b of m is equal to log base b of n, the only way that these two things are true is if m and n are the same number. And then you can solve for the variable. But you always want to go back and check the proposed solutions. Whatever solution you come up with, you've got to check and make sure that it does work. Guys, there's going to be situations where none of your answers are going to work. There are going to be situations when one of your answers will work out of 2. There will be options where both answers will work. It's just different for the different problems. All right, so let's work this one out. We're going to have to get a natural log on one side and a natural log on the other side and make them match. So in this case, we're going to use our properties again to condense this side into one single log expression. So since we're doing a subtraction, that means we're going to end up having a quotient, using the quotient rule for logs. So we're going to have the natural log of the first, x plus 2, over 4x plus 3. And that equals the other side, which is still just natural log of 1 over x. Now, once we know that the natural log of this blob equals the natural log of this blob, then we know that the two blobs have to be equal. Otherwise, this expression can't be equal. So we can drop the natural logs completely. We're not actually dropping it. We just know that for the natural log of this thing to be equal to the natural log of this thing, those two things have to be equal. So we can take that and step away from the natural log expression using just the things in the natural logs. So if these two are equal, we can cross multiply. And we're going to get x times x plus 2, which is going to give me x squared plus 2x, is equal to 1 times 4x plus 3. I'm going to get everything over on one side. So x squared minus the 4x over, we're going to end up with minus 2x minus 3 equals 0. Of course, we're going to factor. Different signs, plus and minus. Largest one is going to be the minus. What two numbers multiply to give me 3 and subtract to give me 2? Of course, that's going to be 3 and 1. So that means we have solutions of x equals -1 and positive 3. And we set each one of these equal to 0 and solve. Now, we've got to go back up here and check our work, check our solutions. Do they work? And what do we notice? Well, -1 plus 2 is going to give us a positive number, so we're okay there. 4 times -1 gives me -4 plus 3, and my spidey sense is going off right now. That would give me a -1 right there, plus the fact that this thing right here. 1 divided by -1 is going to give me a -1 also. So I can't take the log of a negative, and this -1 gives me two negatives in log expressions. The 3 plus 2 is 5. 12 plus 3 is 15 and 1/3, so we're okay on that one. So the only solution we have is x equals 3. So if you have multiple solutions, you always need to check. Actually, not only when you have multiple solutions, but any solution. Go back and check and make sure it doesn't give you the log of a negative number, because you can't do that. All right, that's it.